Okay. So agenda for today is to kind of review undecidability and at least try to prove Rice's theorem, which is kind of a generalization of all the undecidability reductions we've been doing. It's mostly a way to kind of formalize the feeling that some of you already have that, oh, why are all the undecidability reductions looking the same? Okay, and there's a reason for that. So I'll finish by noon so that you can finish the evaluations, and next lecture would be just review. This is the last lecture on content. And what else? If you want to pick up your exam, graded exam, you can either go to the office hours today. Mark has office hours from 2 to 3, I think, right? Or you can pick them up in lab tomorrow or office hours tomorrow. Okay. All right. Let's review undecidability, right? Where were we, right? It's good to have this picture. P, we like P, right? NP, we don't know whether these are, we think NP is not equal to P, and a lot of interesting problems we want to solve are in NP complete, right? That's at the lower level of efficiency, right? P is efficient. NP is contained in X. Every problem in NP has an exponential time algorithm. So, well, we don't like exponential time, right? That's pretty slow. But that's the class X, and NP is in there. And we think NP is actually close to X, but we don't have a proof yet. And then this big red thing is decidable or recursive. These are the problems where we actually even have an algorithm. What is an algorithm that actually correctly gives the answer? We don't care about the running time, but it stops always and gives the correct answer, right? We are relaxing our requirement. Can you even solve it, even whatever the running time, right? It can be doubly exponential, triply exponential, Ackermann function, whatever, right? If you just halt and give the right answer, that's not too much to ask, we think, right? But beyond, but we saw that there are most problems, in the measured sense, are not even decidable. That means we don't even have an algorithm for them, right? Okay, there are many such problems. That is, okay, anything outside recursive is the same as decidable. Anything outside this red thing doesn't have an algorithm, right? It always terminates and correctly gives the answer. And there is a relaxation of recursive, which is like NP. We say what is recursively enumerable. There, we have a program which, if the answer is yes, it will halt and correctly say yes, right? But it may not halt for things that are no, basically, right? So that's the relaxation of what we think of as an algorithm. Why do you want to consider such a thing? What is the use of an algorithm which may not halt? Well, in practice, we do have such algorithms, right? We may have a heuristic for a problem that may not halt in a reasonable time, right? We may still try it on instances, and as long as it is correct when it stops, that is still useful. Yeah, it may not halt, in which case we'll kill the program and say, okay, we ran out of time, right? But if it did halt, it'll give us the right answer. That's somewhat okay, right? And in fact, we do use such programs in practice, right? Heuristics. We run them and we hope they'll terminate in good time. If they don't, we kill it and we say, okay, we couldn't succeed, right? It's like solving homework. We ran out of time, right? So that's one way of thinking about it, right? And people consider levels above that as well, right? Okay, so how do we given we saw, like last few lectures, given a problem, how do we prove that it's hard? Well, the idea is we start with a seed problem that is hard, and somehow we have to have that seed problem, because otherwise coming up with brand new proofs for everything is hard, right? That's not easy. So we start with some seed problem that is already hard, and then we can use reductions, right? I say, oh look, already this problem is hard, so if I want to prove that my new problem is hard, you just reduce the old problem, hard problem, to the new problem. That's the main way we prove new results, right? Easily. You can of course create your own fancy proof, but that's usually hard to do, right? Okay, so what is the seed problem that is hard? Well, the seed problem should have the property that it somehow, why are seed problems somehow the right candidates to try to prove initial hardness? Because they are very general, right? I mean that if it is very general, then it's easier to prove that it is hard. Okay, does that make sense? Yeah? If it is very general, it's easier to prove it is hard. Okay, so that's kind of what is the proof is kind of interesting. Okay, so what is the most general thing that we would like to solve? Well, you know, in terms of computation, the most general thing is this universal language. Given code and an input, will the code accept that input, right? Given a program and a string, will that actually program accept the string, right? That's a very general problem, right? It's a universal problem, right? You know, so that's the universal language, and it is recursively enumerable, right? In the sense that if I want to know whether a program will accept a string, I can actually simulate that program, right? I can just run it, and if it halts, you know, I know what it does, right? If it doesn't halt, I don't know, right? It may not halt, right? Okay, so it's recursively enumerable. And that's what we do, right? You know, if you want to know whether a program correctly thinks, we just run it and see, right? You know, so that's recursively enumerable. But we proved that, in fact, it's not decidable, right? That is, the only way to really check a general program will actually halt and accept a string is to run it. We don't have a magic way of looking at the program and the string and say, I'll think and it'll realize that, this will accept or not. For any one program, maybe we can do that, right? For a custom thing, but there's no one algorithm which can handle it for all programs and all inputs, right? That's too much to ask. We don't have a debugger which is magical, right? You just feed it a program and my input and says it'll correctly say always whether it'll halt or not. That's too much to ask, right? So we know this problem is hard because it's too general, right? Because the inputs, because it's supposed to handle every program and every input, right? That's why it's hard. Okay. So once you have that this is hard, you know, so the picture wise, this language is somewhere here, right? It's not decidable, but it is recursively enumerable, right? It's sitting there. Okay, and then, you know, I can use reductions to prove other things are hard. And what's the reduction? A reduction, as we saw, is transformation of instances of one problem to another problem. If you want to say, we discussed polynomial time reductions, right? X reduces efficiently to Y. If there is a way to transform an instance of X into an instance of Y, and then use the algorithm for Y to solve X, right? This is the box, right? So this is a reduction. When does this reduction make sense? If this whole box actually makes sense, right? What does that mean? You know, for this box to make sense as a solution for X, this algorithm should have the property that whenever it transforms an instance of X to an instance of Y, if this is yes, it should be Y, yes. If this is no, it should be no, right? And then we can use this box, right? Okay, this is a polynomial time reduction if this reduction algorithm runs in polynomial time. But we don't need to insist that it runs in polynomial time. We just say it's a reduction if we don't care how long this takes, right? This is simply saying that, you know, if you have an algorithm for Y, you have an algorithm for X. I don't care about the efficiency here, right? So for NP reductions, we are interested in polynomial time reductions. For decidability reductions, we don't care about the running time. Right? You can take as long, the reduction can be inefficient. Right? All this will prove is that if there's an algorithm for Y, there's an algorithm for X. Yeah, this is a reduction, right? Okay, so once we have a reduction, then, you know, if we want to prove that Y is hard, we take an existing hard problem X and reduce it to Y. What does it prove? Okay. If Y were easy, X would be easy, but we know X is not easy, so Y must also not be easy, right? It's always important to kind of step back and say, am I doing the reduction the right way or not, right? It's easy to get confused, right? You know, so it's not unusual to get confused. You just have to pull yourself back and verify once again, am I doing the right reduction or not, right? Okay. So how do we use reductions? We try to take, you know, we already have a seed problem, and then we can try to prove new problems are hard. So let's revisit the same thing that Lenny did, just to recap what exactly he did, right? You know, maybe do it again slowly, right? What is a halting problem? It's a slight variation of the LU problem. In the halting problem, there is no, I mean, the input is just a code, piece of code, right? And we want to know, if I just run this piece of code, without any input for itself, will it halt or not? Yeah. Just we're asking, will this program, if I just run it, no input, will it just halt or not halt? Right? That's the problem, right? Yeah. What are instances of this problem? Just pieces of code, right? Or a Turing machine, right? And we want to know if you just, the answer should be yes if this program will halt on blank input. And we think it is very closely related to the previous universal language, right? It sort of seems similar, right? Okay. So to make it even more similar, in fact, Jeff defines it like this. Halting problem, he defines it slightly more syntactically similar. What is halting problem in his version? It's very closely related to the universal language. I give you some code and some input, and you have to decide whether that code will halt on that input. Yeah? This is a slightly different version of halting, right? Okay. Okay, so why do we think this is hard? So I claim that the universal language will reduce to this. Okay, but let's forget about the formal reduction. What is difficult about the universal language? What is difficult about this? Right? What is the essence of the difficulty of this problem, right? The essence of the difficulty here is that if I have code and input, I can simulate it, right? Yeah? Okay, if it halts, I know what it does, right? The problem is I don't know whether it will halt or not, right? If I told you whether it will halt or not, a priori, I can use that information and say, oh look, if it is not going to halt, then clearly it is not going to accept the input, right? Okay? So I can immediately say no. So the reason why this is difficult is because I don't know whether the program M on W will halt or not, right? If somebody told me, look, this is not going to halt on W, the problem is solved, right? Because if I know it won't halt on W, I can immediately reject W, right? I know M will reject W. But if I know that M will halt on W, I still don't know whether it will accept or no, reject, right? So I can simulate M on W if I'm guaranteed that it will halt. Yeah? So if I gave you an algorithm which will only tell me on code and input, will the code stop on that input? That's very valuable information. That's the reason why we don't know how to debug, right? We don't know whether the program will actually terminate, right? If you told me whether the program will terminate or not, I can then use that information to say, if it is not going to terminate, I won't even bother simulating it. If it's going to terminate, I will simulate it and see whether it will accept or not, right? So it's easier to see that, the reason why this language is hard is precisely because I don't know whether M will halt on W if I simulate it. Okay. So if I had an algorithm which can tell me whether M will halt on an input W, then I can use it to actually make this decidable, right? Okay. So then clearly that also would not be decidable, right? If that was decidable, this would be decidable, and so we know this is not decidable, so that should not be decidable, right? Halting cannot be decidable. Yeah? Okay. So that's really the intuition, right? The reason why checking whether a program will accept a string is difficult is because we don't know whether it will halt or not, right? So that's really the essence of the hardness, right? Okay. So, but we still want to, for technical reasons, even though we understand the intuition, we want to simply think about this slightly more restricted problem where I only give you code, and the problem is to decide whether that code will halt on blank input, right? And we want to do a reduction which is a little beyond just simply intuition, right? I want to claim that this problem is hard, and how am I going to prove it's hard? I'm going to say, look, I'm going to reduce from the existing hard problem, which is LU, and I'm going to show that, if you had an algorithm for halt, you can get an algorithm for LU, and since we know this is not possible, this also must not be possible, right? Okay, so let me show a box, right? Okay, let's see if I have that in the, okay. So how are we going to do that, right? So if you want to do this, right, we need a box like this, right? Yeah, what does it mean? That the reduction should do what? It should convert an instance of LU into an instance of halt, right? So what is the instance of a LU? It is a program and a string W, right? Yeah. What do you want to know? Will this program accept that string, right? Okay. So to know that, what we'll do is we'll convert this. Our reduction should convert this into just one piece of code, right? Yeah. And then we should give that piece of code to an algorithm which will only tell me whether this piece of code will halt or not, right? And from that information, I should be able to figure out whether this M will accept W or not, right? If you can do that, then I know that I've reduced LU to L halt, and since this is hard, that will be hard. Yeah. Okay. Okay. So here is, okay, so let me give you an example, right, of how the reduction goes, maybe with the concrete code, right? Okay, so suppose I want to check, I wrote some program called is prime, right? What does it do? It takes an integer and checks whether it's a prime number or not, right? Okay. I want to know whether is prime will actually accept 13 or not, right? That's the problem I'm trying to understand, right? I have this code is prime. I don't know what it does. It's a complicated piece of code, right? It could be a complicated piece of code, and I want to know, I have the code with me, and I want to know, will it accept 13 or not, right? Yeah? Okay, but I know it's a hard problem. Checking whether a program will accept a string is hard problem, right? But so you tell me that you have a nice super duper debugger, but it's a little bit restricted debugger, right? All it will do is that if you give it a piece of code, it doesn't want any input, it will just tell me whether it will, that piece of code on running on blank input will halt or not. Okay, I'm trying to use your super duper thing to solve my problem, right? Yeah, but it's super duper, but only a slightly restricted way, right? It's not solving exactly what I want, right? So I want to convert but I know somehow it's essentially capturing what I want, right? So I want to take my program, which I want to check whether it will accept 13 or not, convert it into another program, right? And just feed that program into your fancy algorithm and get my answer, what I want, right? That's what I'm trying to do. That's what a reduction is trying to do, right? It's going to twist what I want to solve into something that is in a format that your algorithm can accept, right? Okay, so here is what I write, right? I write this new code, right? Remember, I have the code for my is prime is a piece of code, right? So what I will do is, I'll create a new program like this. What does it do? It just, remember, I'm writing code. I'm not running it. I'm just creating this program, right? So this program looks like this. So it says, okay, it will make my original code is prime into a subroutine, right? Right? Remember, I have the code, right? It puts it as subroutine, and in here, this code will say, if is prime 13, then quit, else loop forever. Yeah. I just wrote this 5 lines of code, right? And then I appended my existing code into a subroutine like this, right? Can I create this code from, if I had the code from is prime? Easy, right? I just am writing few lines, right? And then tacking on my code, okay? What is the property of this new program? What can we say? Sorry? Yeah, so when will this program halt? Only if is prime 13 will return true, right? Yeah? Okay, otherwise it will loop forever, right? Okay, it makes sense, right? So if I had if I can feed this to your fancy algorithm, which will tell me yes or no, right? If it tells me yes, I know that is prime will actually accept 13. If it tells me no, I know that is prime won't accept 13. Yeah. So if you had a nice program that can just take code and say yes, it will halt or not, then I would know whether is prime will actually accept 13 or not, right? So that's it. That's all the reduction is doing, right? So what did the reduction do? The reduction produced this code, right, from this code, right? But that's almost, in fact, linear time, right? You just dump this, instead of this being the main program, you made it a subroutine and you just added these 5 lines of code, right? You just took one piece of code and created another piece of code, right, by adding 4 lines, right? Okay? Yeah. Example is much more clear, right? But see, this is all this is doing, right? Okay, so it's better to understand it this way, right? And it's not special to is prime, right? Given any program and any input, if I want to know whether that program will accept that input, I just do this thing, right? I just make my original program a subroutine and create a main program and run it on that, and right? Agreed? So that's all, right? We've reduced universal language to halting, right? So this proves that halting is hard, because if you can solve the halting, then universal language also will be easy, right? Any questions on that? Is it clear by now? Yeah, this reduction, yeah? Okay? Right? Okay. So that's, I'll skip the, so this is what it is saying, right? This is creating a code for this, but it's much easier to understand, okay? So let's do a couple more of this kind of reductions, and then we can make sense of why people are like, Rice's theorem makes sense. Why did somebody create a theorem out of these kinds of things, right? Kind of interesting to see how theoreticians think, right? Because, the point of theory is to reduce, to overuse the word reduce, right? Our knowledge into the smallest number of statements we need to remember, right? The point of theory is to do that, right? To condense our knowledge into a format. And how do we do that? By generalizing, right? Instead of saying, I want to remember 2,000 facts, we want to remember only one theorem, which captures all those facts, right? In a compact form, right? That's the job of theory people in some sense, right? Okay. So let's look at this language, right? What is this? This is a set of all programs that accept only a string of 374 zeros. Okay. Or maybe this is more interesting. Let's do this, maybe more interesting, for it makes more sense maybe. So I wrote a code for checking whether a string is a palindrome or not, right? Okay. Okay. I gave an exercise, and you want to know whether your code actually does that, right? So what is this language? This is all programs that accept only palindromes, right? So basically, this is if you had a algorithm to solve this language or this decision problem, then you'll have an auto grader for the assignment, right? Where I gave an assignment in 125, write a piece of code that will check whether a given string is a palindrome or not, right? Okay, they will see that this is an auto grader for that assignment, yeah. Okay, so it would be nice if I can write an auto grader and not actually grade all your homeworks, right? So I'm going to try to convince you that no, I can't write an auto grader so easily, right? Because you can give me very fancy code, right? Yeah, that's a problem, right? I want to know, I ask you to write a piece of code which will check whether a given string is a palindrome or not. And you say, and I claim that I have an auto grader, and you guys can be very clever and say, these guys are stupid, they don't know what they're getting into. And you can shove gold back inside your thing and let me see what they do, right? Is what you can, right? A clever undergrad can do that. That's really the problem, right? I cannot tell what you put in your code, right? You can put whatever mathematical theorem inside it, and before you do anything about palindromes, right? So then my autograder should actually tell yes or no, right? But then I'll be solving a mathematical theorem, right? Which is hard, right? So that's the problem, right? So that's essentially all of these reductions, right? Let's do the palindrome, right? That is maybe okay. So what will you do, right? So I'll reduce LU to L palindrome. What does it mean? Suppose you had I claim that there is no algorithm to check whether a given piece of code has the property that it will only accept palindromes. Yeah. So how do I do that? I want to convert. I want to reduce from LU to LPAL, right? That if you had an algorithm to check whether a given piece of code will only accept palindromes, I will be able to use it to solve whether an arbitrary program will accept an arbitrary input. Yeah. How will I do that? Well, I have to give you a reduction which takes an arbitrary piece of code and an arbitrary input string W and convert it into a program, right? And give it to the supposed algorithm which will check whether that program will accept only palindromes, right? Yeah. Okay. So what should that program be? So that program is this, right? This. Okay. So what it does is, remember it makes this. This is think of this as is prime and W as 13, right? So I have that, and I want to check will is prime accept 13 or not, right? But I don't have a direct way of checking it. But we have an algorithm that given any program will check whether that program will accept only palindromes or not, right? So okay, I see halting problems, right? Okay, so what should that program look like, right? So what it will do, just like what we discussed, is that it will first run, it will make this is prime and 13 as part of its code, right? It will first run is prime on 13, okay? Right? Before it does anything, it will just run is prime on 13, okay? And if it accepts, then it will accept its own input x if it is a palindrome. Okay, so this is given is prime and 13, we can create such a piece of code, right? Yeah. What does it do? It first runs is prime on 13 and then checks whether its input is palindrome or not. And if it's a palindrome, it will accept, otherwise it will reject. Yeah. So this piece of code, let's understand what it does. What happens with this piece of code? What is its behavior? It's a very simple program, right? What does it act? What is the language accepted by this code? If is prime accepts 13, what does it do? Then it accepts all palindromes and only palindromes, right? Yeah? Agreed? If is prime accepts 13, then it is doing the right thing, right? It checks whether the x is a palindrome or not. Yeah? So the language of this code is precisely the palindromes if is prime accepts 13. If is prime doesn't accept 13, what does it do? Will it do anything? Well, it will not accept any string, right? Yeah? Because, if is prime doesn't halt, it is not going to accept its own input. If it halts but doesn't accept 13, it is going to reject everything. Yeah? Okay. My claim is that the language of this code is empty if is prime does not accept 13, is precisely palindromes if it accepts 13, right? So if I had an algorithm which can tell me whether this code is going to accept only palindromes or not, I would know whether is prime will accept 13 or not, right? Yes? Yeah, no? Kind of confusing. Okay, the whole point in this reduction is that you only have an algorithm which checks whether a piece of code is going to accept only palindromes or not, right? But I want to answer, I'm not interested in checking palindromes. I'm interested in knowing whether, is prime will accept 13 or not, right? But the point is I can shove is prime into my code. I mean, checking whether a string is palindrome is easy, no? Yeah? I mean, I can write code for that. Correct code for checking whether a string is a palindrome is easy to write. okay? But inside it, I can put a subroutine for some complicated code that I want to check, right? So if you had a magical box that given a piece of code can check whether that code can is only accepting palindromes or not, I can shove something complicated, and if you can debug that piece of code, then I can actually know what the original program is, whether is prime will accept 13 or not. Okay? All right? Yeah? So let me, I mean, maybe one more example so that to just tell you that these are all the same reductions, right? So let's look at this language, right? What is this language? This is a set of all machines or code that accept precisely this string 0 to the 374, right? Okay, is this language clear? What is this language? This language is like, I'm interested in machines which only accept one string, 0 to the 374, okay? You can create a DFA for this, right? There's a DFA which accepts just this string, right? Because a finite language, you can create a DFA. So you don't even need very complicated code for this. But if I tell you, is this program only going to accept that string? It's a hard question because code is complicated, right? Okay. Okay, again, so here is a reduction, right? Which says, if you had a box which given a piece of code will tell you yes or no correctly for whether that program accepts only 0 to the 374, then you can check whether any program will accept any input, right? Okay, so let's think about this thing, right? What does this code do, right? It's easier to understand more concretely. What do you think this code does? See, remember this code takes its own input, right? X, yeah? So what do you think this code does? What is the behavior of this piece of code? Yeah. Right, so this code, as I said, what are the strings it will accept? So okay. So if is prime 13 does not halt, what does this do? Will it accept any string? No, right? So if is prime 13 does not halt or does not accept 13, right? This code will accept nothing, right? Yeah? Agreed? Okay, but if is prime 13 it will accept, what does it do? It only accepts 0 to 374, right? So the language of this code, or what the language of this code is empty if is prime does not accept 13, right? Is exactly 0 to the 374 if is prime accepts 13. Okay, so knowing these two, we can check whether is prime will accept 13 or not, right? Yeah, if somebody can magically tell us whether this language of this is empty or exactly what we want, we can check whether is prime would accept 13. And there's nothing special about is prime and 13. I can shove any piece of code and any input here, and your algorithm will help me, right? Okay, so that's it. That's it. All reductions are like that, right? So what is this? The essence of this is that here is the essence of that, right? Okay, there are a lot of things that are undecidable, right? Okay, so let's make sense of what is going on here, right? And that is so here is Rice's theorem informally, right? What does Rice's theorem says? What can we decide about the languages accepted by programs? Answer is nothing. Okay. Okay, so what this is saying is, okay, it's worthwhile to spend some time making sense of this, right? See, there can be many programs that achieve the same goal, right? Yeah, I mean, we all write different code for the same task, right? So effectively, the problem of checking whether a given piece of code has some property is kind of hard, right? Okay, but to make it formal, it's not as, understanding Rice's theorem, the statement, not the proof. The proof is not hard, but it is one more level of abstraction, and it's you have to sit down and think about it. But let's try to understand the statement of what it is saying, right? That itself is not obvious, how to make sense of Rice's theorem, right? So for that, we have to understand what is this really saying, what is a property? Let's make sense of that. Okay. So a property of RE languages, right, okay, is simply a subset of the RE languages. Or another way of saying this is the following, right? Does this language, suppose I say, is this language finite? Right? What is the answer? Yes or no, right? So the property of a language is simply, when you say, this person is tall, what are we saying? Right? We are taking all the people and classifying into those who are tall and those who are not tall, right? Okay. Same way, if you take all the recursively enumerable languages and say there is some property of these recursively enumerable languages, we are implicitly saying that some of these languages have this property and some of these languages don't have this property. Yeah? Okay. So a property is nothing but a partition of the set into two things, right? Those which have the property and those which don't have the property. Yeah. Okay. So here is some properties, right? L contains 0 to the 374. That's a property, right? Why is that a property? Some languages have that, some languages don't have it. Yeah. Okay. L is finite. That's a property. Yeah. Yeah. And L is empty. That's a property, right? Okay. So okay. Now we are interested only in recursively enumerable languages, so we want to kind of say the following, right? Take any property, interesting, or any property in fact, right? So let me say what the trivial properties are. When is a property trivial? A property is trivial if every language satisfies it or if every language does not satisfy it. Right? We're not interested in trivial properties, but let's look at some trivial properties. Look at all the strings, all the programs such that the language accepted by that program is recursively enumerable. Why is this trivial? Why is this property trivial? Because by definition, every Turing machine accepts a recursively enumerable language, right? So all languages satisfy this property. Okay. So look at all the programs such that L of M is not recursively enumerable. That's also trivial. Why? Yeah. Because the complement of this, right? No string satisfies the property, right? Okay. Look at all Turing code such that the language accessible by that code is empty or is not equal to empty. Why is that trivial? Sorry? It's always true, right? Right? Includes everything. Okay. So trivial properties are not interesting, right? In the sense that we're not interested in trivial properties. If everything satisfies it or everything doesn't satisfy it, why are we interested in that property? Right? Okay. All right. So trivial properties are not interesting. So I want to claim that non-trivial properties are undecidable. What does that mean? Okay. So take any property of recursively enumerable languages. Like take an example. Is the language accepted by this machine finite? Okay, that's a property, right? That's not trivial, right? And now I claim that the problem of deciding the following. given a piece of code, checking whether the language accepted by that code is finite is undecidable. Okay, does the statement make sense? So I want an algorithm which, if I feed a piece of code, will tell me whether the language accepted by that code is finite. That's a hard problem, it seems, right? That's undecidable. Yeah. Okay. So now I can. What did we see earlier? We said, given. Let's look at the property that the language accepted by that machine is basically all palindromes, right? That's a non-trivial property, right? Because some languages, some machines satisfy that property and some machines don't satisfy that property. Okay? So Rice's theorem basically says that every non-trivial property is undecidable. Okay? So that's not so what can we conclude from that, right? So basically it says that, if you have anything interesting about the language accepted by a machine, you can't tell whether there is no algorithm which, given a machine, will tell you whether that language accepted by the machine satisfies that property, right? So I mean, maybe it's best to skip the proof and just understand examples, right? Of why that theorem is general. So given M is L of M equal to palindromes. Why is that undecidable? Because maybe take this, right? Given M is L of M equal to empty. Why is that undecidable? Right? Using Rice's theorem. Okay. The property of the language being empty, not empty, is a non-trivial property, right? Okay. Some machines have it, some machines don't have it. Okay, and so it's a non-trivial property, and so this is undecidable. Okay, given M is L of M equal to 0 to the 374. Why is that non-trivial? Because some machines have that, the language accepted by some machines have that property, and the language accepted by some machines don't have that property. So it's a non-trivial property of the language accepted by the machine. Okay, so any such property is undecidable, right? That's the content of Rice's theorem, right? So it is not surprising that all the reductions look the same. Okay, because there's a meta reduction which will prove that any non-trivial property is undecidable. Okay, so that is I won't go through the proof because I think it's a two-level abstraction which is already complicated. So if you're interested, you can okay, what I would like to tell you is that make sure that you don't confuse Rice's theorem to saying that it will capture everything that we want to capture. Okay, so here are some nice questions, right? The definition of Rice's theorem here, P is a property of the languages, not the machines themselves. So we are really careful. Take this problem. Given a machine M at some times moves its head to the left. Okay, is that a property of the machine or is it a property of the language accepted by the machine? I claim it's the property of the machine, not the language accepted by the machine. Okay, so look at this, right? I give you a Python program and I ask, does a Python program have 374 lines? That's easy to check, right? Yeah, that's not a property of the language accepted by the machine or the code, but it's really a property of the code itself, right? What about this? I give you code and ask you, does it print hello world? That's a property of the language accepted by the machine and not the machine itself. Okay, so Rice's theorem applies to properties of the languages accepted by machines, but not this kind of stuff. This doesn't come under Rice's theorem, right? This is easily decidable, right? Yeah, I mean, I can check whether the program has 374 lines or not, but what I cannot check is whether code will have certain behavior, right, when it is run. Okay, so you have to be a little careful about that. So properties about the code itself are sometimes decidable. For example, code has 374 lines. That's decidable, right? It's easy. If I give you a piece of code and check, does it have 374 lines? Yes, it is easy to decide. What about this? This is more interesting. Okay, I give you a piece of code and I ask you, if I run it on a blank input, will it use less than 374 tape cells on its when it's run on blank input? Okay, I say, you know, I take a piece of code and I'll ask, if you run it on a blank input, will it use less than equal to 374 tape cells? Or will it need to use more? Is it decidable or not? Okay, so let's worry about not tape, right? You know, I give you a program, okay, and I want to ask you, will it actually use more than 1 gig of memory? If I run it, will it use more than 1 gig of memory? Can you decide whether that will do it or not? I claim it's decidable, so it's a trick question, right? Why is it decidable? What can you do? Suppose I start simulating it, what can happen? I can simulate the program, right? And I check, right? What can happen if I simulate it? If it uses more than 1 gig, I can keep track of, right, whether it is using more than, how much memory it is, right? If it uses more than 1 gig, I can stop it, right, and say, aha, you used more than 1 gig, right? Okay, but what if it doesn't use more than 1 gig? It can still go into an infinite loop, right? Okay, but something is special about it, right? Can I detect whether it can go into infinite loop? I claim I can. Why? Yeah? Exactly, right? So if I am constrained to use less than 1 gig and I am going into an infinite loop, what must have happened? How can I go into an infinite loop if I am not using more than 1 gig of memory? Sorry? I must repeat my state, no? So think of my program state as where I am in the program and the contents of the memory, right? How can I go into an infinite loop if I am not exceeding memory of a fixed length? I must have gone into an infinite loop because I go into a state and I loop back to the same state, right? And there's no way to get out of that, right? Because I'll repeat my behavior because I'm, right? But that I can check, right? Because, I mean, this is not practical, but what I can do is, I am simulating you, right? And I can have a huge memory, more than 1 gig, right? I store all your states, right? Yeah, because I know, I mean, if you exceed 1 gig, I'll stop you, right? But if you're not exceeding 1 gig, you keep running this, right? I hash all your states, right? If you ever repeat a state, I know you have gone into an infinite. Yeah, does it make sense? So this problem is decidable, no? Yeah. Okay. Agreed. So in practice, people use these kind of tricks, right? That the way people check whether a program goes in infinite loop, the reason why it is hard in general is because the memory also can grow, right? I could just keep going, and how could I keep track of a state, right? But if you're constrained to use only a small amount of memory, I can keep track of the entire state. At least theoretically, you can do it. So this is decidable. Yeah. Any questions on that? Yeah. Make sense? So okay. So what about this question? M never moves head to the left. Is that decidable or not? I claim it is decidable. Why? I can look at the code, right? And if it has, if it has any move which moves the head tape to the left, I know I can create an input which it will move to the left. If the no moves of the machine I ever move to the left, I know the answer is yes. Otherwise, I know the answer is no. I can just look at the code and tell you the answer is yes or no, right? I don't have to do anything. Yeah. So I can make it go to that state. I can check that. Whether there is some way of getting it. Using reachability, I can check that. Oh, sure, yes, but I'm not asking it on a specific input, right? On blank input, I'm asking. Oh, yeah, right, right. So on a blank input, I can check. Yeah, this is a tricky one. Yeah. Okay, so sometimes it's undecidable, right? See, M halts on blank input is it? It is not about the language of the machine, right? It is really about the machine itself, and this is undecidable. That's the halting problem, right? Okay. So M on input eventually writes 2. This is not also about the language because it is just procedural, right? There is nothing about the language. It might do some funky thing about the language, but you're asking, will it ever write 2 on this particular input? That's not about the language of the machine, but it's the machine's behavior, right? This is also undecidable, right? Okay. So I'm trying to make sure that you don't get confused by Rice's theorem. Yeah. Sorry? No, not really, right? Yeah, I mean, what does it mean, writes to? It's basically, it's just clarify that it's eventually, right? Yeah. Okay. So anyway, in any case, the Rice's theorem is just a philosophical theorem, right? To kind of help you make sense of why many of these theorems look similar, reductions look similar. But I suggest not to get confused with Rice's theorem, okay? All right, because, for example, you will not be able to prove that these kind of things are undecidable using Rice's theorem. They don't fall under the purview of Rice's theorem, even though we are able to prove these problems are undecidable. Okay? So really what you need to remember to prove that a problem is hard is to be able to reduce it from an existing problem. Right? And there are only 2 things that you really need to remember. Right? What are we always reducing from? Either halting or the universal language. Okay? Given a problem that you want to prove is hard, undecidable, you just reduce it from the universal language or the halting problem. Okay? Rice's theorem is just a way for you to, if you are interested, to realize that there is a reason why all these reductions look similar. Okay? But understanding it, applying it correctly could be hard. Okay? So, but you need to remember, right? This idea. If you can remember this idea, that is all you really need, right? Think of it this way. If right? It is useful for you to not maybe be so abstract, but you sort of say, if I want to check a given program does something, I can create new code like this. And if I knew that how, the idea is that, if this is prime will accept 13, I will have some behavior. If it doesn't accept 13, I'll have some other behavior, right? And so writing this code is very easy. Now you have to figure out, given that I have a black box to answer some interesting question, can I fool it into answering a more difficult question, right? By creating code. That's what you need to remember, right? All right. So the rest is the Rice's theorem is complicated. Yeah. But if you're interested, you can read it. Yeah. Agreed? Any questions on undecidability reduction? Does this help to have this concrete code like this? Yeah. Right. If you're confused about the abstraction, think like this. Right. Write down, like, relate what you're trying to solve by writing concrete code like this. That'll help you. Yeah. Okay. Sounds good. And so let me finish up with some philosophy, right? All right. The course has been hard. I know many of you find it difficult, but it's hard for me too, right? I struggle, right? But I think algorithms and theoretical computer science are foundations of computer science, right? What does it mean to compute? Why are some things difficult? Why are some things easy? And algorithms are non-trivial, right? They're clever and interesting too, right? And it's just not just pragmatic. Of course, the main thing we do reason we do algorithms is because they're useful in practice. But they're also very closely connected to a lot of other things like math and physics and biology, chemistry, social sciences. It's how do we model what people do, game theory, ad auctions, right? How to, if you do what's going on behind the algorithms for ads, it's a combination of social sciences and algorithms. Right? So computer science is as you know, is becoming a hub for many things ranging from humanities to natural sciences. So, and one of the ways it becomes a hub is through modeling, theory, algorithms, and limitations, right? And some of you are interested in theory, and some of you are like, no more theory, right? But if you are interested in algorithms and other theory courses, there's a list. You can take Theory 2, which is 473. It's offered every semester. You can talk to friends who might be taking it to see what it's like. Some of you may be more interested in complexity. I know a few people. There's a graduate level computational complexity course, but there's an old 475 which is being resurrected this fall by Mahesh, which will have complexity theory and things like that at the level of 400. So it might be more suitable for some of you. We teach many courses like randomized algorithms, approximation algorithms, complexity, and we keep teaching special topics: game theory, data structures, geometry, big data algorithms. We have a new faculty member coming who's going to teach about pseudo-randomness, combinatorial optimization. Okay, many courses you can take a look if you're really interested. Okay, and theory pervades many other areas, right? Machine learning, right? There's a lot of theory, algorithms, continuous optimization, right? And there's a separate part of theory on logic and formal methods, right? If you're interested in that kind of stuff, programming languages, that's a different take on theory. And some of you take graph theory, combinatorics. There's a lot of theory in even ECE, right? Coding theory is all algorithms for a particular problem of encoding and decoding information. Okay, it's really a lot of algorithms inside that, right? Information theory is full of theory. Signal processing. Underneath that, there are a lot of actually thinking about them algorithmically is very useful, right? And there is a lot of algorithmic work in computational biology. Some of you may be interested in biological aspects, and we have several faculty in our department who do computational biology now, right? Tandy Warnow does a lot on algorithms for computational biology, right? Okay, I know grades are important, right? And it's been a tough course, but I hope you learn something about thinking analytically about problems and having an edge over other people who can also program, right? Right? Computer science is many things, right? You have to be able to program, you have to be able to design, you have to be able to understand the systems, engineer, and things like that. But one skill is to think formally, model formally, prove correctness, and be efficient, right? And you cannot do that without being somewhat technical, right? And so, the way to differentiate yourself is, as computer science students, is to be stronger in things that other people with less training can be strong at, right? Everybody in the world can program these days, right? High school students can program, right? So what is the value of your degree if you cannot do something that they can also, right? So you have to develop some edge by some way, right? And that's not just pure programming or hacking, right? You need to have other skills too, right? At least in the long term, all right? Okay, and I teach, I try, right? But eventually, learning is tough, right? Learning, you have to do it mostly on your own, right? With the help of resources like notes, or lectures or something, right? But I like this quote because, without one's own attempt at understanding, nothing goes in, right? By doing and by struggling, that's where you learn, right? So we try our best, but eventually it's up to you, okay? Thank you, and I will leave this here. I need a volunteer to return it to the academic office. Can somebody volunteer? Okay, you want to volunteer? Thank you. Return the pencils to if you can. They like to get their pencils back. You just take a few minutes, give me constructive feedback on, you know, what you enjoyed, what you didn't enjoy, what worked well, what I could do better, and you know, it'll help their fellow students who are coming after you. So, I mean, you should come here. I mean, I'll pass this on. Okay. Yeah, I think there are too many here. Not too many of you come to lecture. So, so take one, fill it out, and I will. So, the next Tuesday is basically review. So I'll just do review for the finals, like we do normally for exams. Okay. Academic office, no one will see this. Yeah, any seats.